Welcome to another session on optical communication. I'll just give you a recap of what we had seen in previous class. Then we'll move on to the next topic, which we are going to see in today's session. In in the last class, I had given you an introduction to optical fiber communications, introduction to all the 5 units, then introduction to the unit 1, and we had seen the evolution of fiber optic system and the element of an fiber optical transmission link. These two concepts we had seen. So in today's class, we are going to see the ray optics, optical fiber modes and its configuration, linearly polarized modes, single mode fibers, and graded index fiber structure. Okay. So let us move on to the today's class, which is ray optics. I hope the presentation is visible to all. Is presentation visible? You can type in chat box, no issues. If it is not visible,
Visible, sir.
okay. Thank you, Mukesh. So to start with today's class, it is ray optics. So this ray optics is the basic laws which have been used for fiber optic communication. So, so what does this ray theory or geometric optics gives information to us is that in a homogeneous medium, the light rays are always straight in nature. Homogeneous medium in the sense the core and cladding will have the same refractive index. When a light passes through them, it travels in a straight line. Okay. So that is what homogeneous medium. All the RI or the refractive index of both the mediums will be same. So that is the first law. Next law is that light, when it travels through the optical fibers, gets absorbed or reflected. Either the cladding material will tend to absorb the light signals or it will tend to reflect the light signals depending upon the refractive indices being used for the cladding. Okay. So next is that reflected ray, if the light which falls, if it is reflected and lies in the plane of incidence, and the angle of incidence will be equal to angle of reflection. If the reflected ray lies in the plane of incidence and the angle of incidence will be equal to the angle of reflection. So theta I is equal to theta C. That you would have studied in your engineering physics. Same law. So next law is that at the boundary between the two medias, that is medium 1, medium 2. As you had studied in electromagnetic waves and fields, dielectric boundary condition or magnetic boundary condition. E and T as is same as inside and outside. B and D is same as inside as outside. The same boundary condition. Okay. At the boundary between the two media of different refractive indexes. Yes. See here, the media is a medium having different indices. Refractive indexes are different. So, in this case, the reflected ray will lie in plane of incidence. Next law is your Snell's law. So this Snell's law gives the relationship between angle of incidence and angle of refraction. Angle of incidence and angle of refraction. So that you have studied. So first let us see refraction of light. I think you are familiar with the terms called incidence, reflection, and refraction. So if you are familiar with these three terms, then this will be much easier to understand. So as light passes from one transparent medium to another, so you can see that arrow mark indicates the flow of your direction of light in red color. So light is passing from one medium to another medium. Medium 1 is air, medium 2 is water. So I have a normal correspondence to that. So where the air medium and the water medium gets meted. So here you can see that medium 1 is air and medium 2 is air. So where these two meet and where this light falls is taken as a normal point. Okay? So that is your point of boundary. Point of boundary. So when light falls or passes from air medium to water medium, you can see that it changes its direction. It is not as it is. So it changes its direction. So this phenomenon is called as refraction of light. Refraction of light. So how much angle it changes? So how much? What is the direction of change in the angle of the propagation of light? Depends upon the refractive index of the medium. So this is just an example. So refractive index of the medium determines the direction. Of light propagating from one medium to another medium. So next is the refractive index. So refractive index measures how much a material refracts light. Okay, how much a material can refract. So the refractive index of material can be obtained by N is equal to C by V. Okay, C by V. So C is velocity of light in vacuum, which is approximately 3.8 into 10 power 3 into 10 power 8 meter per second, which is abbreviated as C is equal to 299,792.458 kilometer per second. Divided by V is the speed of light in that material. So what material we are taking? For example, if you are taking water, what is the speed of light in water? If you are taking wood, speed of light inside wood. If you are taking kerosene, speed of light passing in kerosene. So that is your V. Whatever material we take, that becomes your V. Okay. So 3 into 10 power 8 meter per second divided by that speed of light. So which gives you refractive index. So this is the definition of refractive index. So next we'll see Snell's law. So Snell's law, as you all are familiar. So I take the same air and water as medium 1 and medium 2. Air is having a refractive index n1, water is having refractive index n2. So when light passes from one medium to another medium or from air to water, it bends according to the Snell's law. So the angle being created with respect to the normal in medium 1 is taken as theta 2, and the with respect to the medium 2, with respect to normal in medium 2 is given as theta 2. Okay, so then the Snell's law can be given as n1 sine theta 1 is equal to n2 sine theta 2. So what is this n1? As we had said, refractive index of medium 1. n2 refractive index of the material. Here in the case it is water, and medium 1 is air. So n1 is the refractive index of the medium, the light is leaving, and the medium is air. n2 is the refractive index of the material, which is water, where the light is entering. So then theta 1 is the theta 1 is the angle, and specifically incident angle, which is being created between the light beam and the normal. So this normal is 90 degree to the interface between two materials. Okay, theta 1 is the angle between light beam and the normal. Theta 2 is the refractive angle between the light ray and the normal. So this is your Snell's law. So next is that critical angle. Okay, so critical angle. So critical angle can be calculated easily from Snell's law, putting an angle of 90 degree or the angle of refractive, which is theta 2. Okay, so critical angle can be found out by making the theta 2 as 90 degree. Let's see that theta 2 as 90 degree. So then what is that? Since theta 2 is 90 degree, sin 90 will be 1. Critical angle will be theta c is equal to theta 1 sin n2 divided by n1. Okay. Recall this formula. n2 so n1 sin theta 1 is equal to n2 sin theta 2. Theta 2 is 90 degree, so which is 1. Then 1 into n2 will be getting n2. So sin theta 1 into n1 is equal to n2. So on rearranging, we can find the critical angle as critical angle will be equal to your angle of incidence, which is theta 1, which is n1 n2 arc angle of n2 by n1. This is how to determine critical angle. Next is numerical aperture. Numerical aperture. Numerical aperture by using this formula nf square minus nc square. Okay, what is nf square minus what is nc square? Okay, n, first of all we'll define n. So n is the refractive index of the medium light. Okay, medium light before entering the fiber. So we have a fiber, so the light enters through this fiber. So before entering the is n. So when it enters the fiber, what will happen is that due to the presence of optical fibers, core and cladding, So the core will be having a refractive index which is NF given as, and the cladding will have a refractive index NC. You can label this in different way also, N1 and N2 also, it doesn't matter. So here I'm taking NF NC. So the square root of NF square minus NC square is equal to the numerical aperture. So this is how to determine numerical aperture. So for step index multimode fibers, the angle is determined by excess of refraction. The excess of refraction are being calculated by refractive index of the core and refractive index of the cladding. This is the total internal reflection. Total internal reflection. So you can see same type of two mediums. Here I am going to take the medium 1 as glass material, medium 2 as air material. Okay, since you are going to deal with the optical cables here afterwards. Okay, so you all are familiar. N1 is refractive index of medium 1, N2 refractive index of medium 2. So this N1 can be given as NF also as in determining a numerical aperture. N2 can be given as NC as given in numerical aperture determination. So N1 is equal to 1.5, which is refractive index of glass. N2 is equal to 1, which is the refractive index of air. So when a light passes from medium 1 to medium 2, that is from glass medium to air medium, what happens? Okay, we'll see that. So if the light hits the interface at any angle larger than its critical angle, so critical angle is that 90 degree, okay, larger than its critical angle, it will not pass through the second medium at all. Okay, you can see that the blue color here. Here the red represents your critical angle. Okay, 90 degree. So with respect to the normal, this theta c is a critical angle. So if the light hits the interface at an angle larger than critical angle, it will not pass through the second medium at all. Okay. Instead, what will happen? It will reflect back to the first medium itself. You can see here. This blue color is that. The blue color, when it falls on the boundary, it reflects back to the first medium. Okay. And if it is less than the critical angle, it will easily pass through. Okay. If it is the light falling, which is in green color, light falling on the boundary. If it is less than the critical angle, it will pass through that medium. Okay. So this process, which is indicated in blue, okay, indicated in blue, is called as total internal reflection. I repeat it again. If the light hits the interface at any angle larger than this critical angle, it will not pass through the second medium at all. Instead, all of the light will be reflected back to the first medium, which is known as total internal reflection. So by using this total internal reflection formula or principle, the optical fiber transmits your optic signals from one place to another place. Okay. So any queries or doubts in this ray optics, Snell's law, or total reflection? If you're
No,
having
sir.
any in chat box, in another 2 or 3 minutes, I'll proceed on to the next, which is types of fibers. So any queries, type in chat box. Yeah, somebody called Naresh Reddy is coming outside the SUSME link or outside his official email ID. Inform him to use his personal, sorry, use his official email ID for attending
Okay, sir.
classes, or not to use personal mail IDs during class sessions. Okay, since no queries, and, thank you Mukesh, thank you Kirtan. Okay, we'll proceed, Satvika. Okay. So after the ray optics principles, Snell's law, total internal reflection, numerical aperture determination, we're going to see fiber optic modes, which are the basic types of fibers. Okay. So first of all, we had seen the fiber optics. We had seen its principles, how it moves. So what is this mode called as? So mode is one which describes the nature of propagation of electromagnetic waves in a waveguide, so which we had seen in electromagnetic fields. Okay, a mode is one which describes the nature of propagation of the electromagnetic waves inside a waveguide. That is, it allows the wave to propagate with its associated informations, whatever might be. Okay, for example, if you see your electromagnetic wave would have transversed, you would have used TE modes, TM modes, and TEM modes in different configuration: TE10, TE01, TM01, TEM mode, and so on. So in that, the electric field and magnetic field E and H will be perpendicular to each other always, and the direction of propagation will be perpendicular to both of them. Okay, so that is what here it is called as associated contacts. Okay, so this was what we had done in electromagnetic waves. Okay, E and H that is what electric field and magnetic field were transverse in nature, that is perpendicular to each other, and the direction of propagation was perpendicular to both of them. Okay, there it traveled. But here in fiber optics, the same mode is being given as mode is the one which describes the nature of propagation of optical wave inside the optical fiber. Okay. So based on the number of modes that propagates through the optical fiber, they are classified into single mode or multi-mode. So, for example, if I have an optical fiber cable and it can assess or it can send only one mode with one frequency or one signal, we call it a single mode. And if there is another optical fiber, it supports transmission of signals at multi-modes or many signals. We can use this multi-modes. So based on the number of modes that the fiber can transmit, they have been classified as single mode or multi-mode. Okay. What is this single mode fibers? Its specifications and how to determine its refractive index. Okay, so single mode fibers. In a fiber, if only one mode is transmitted through it, then it is said to be a single mode fiber. So a single mode fiber will have its own dimensions. Okay, it should be specified in this format only. It should have a core radius of 3 micrometers, core radius 3 micrometers, numerical aperture of 0.1, operating at 0.8 micrometer wavelength. And the condition for single mode operation is the V number of the fiber should be less than or equal to 2.405. So this is the condition for a single mode fibers to be designed. Okay. So here we will be having the information of the core. So which is refractive index of the core as N1, A as radius of the core, lambda as the wavelength of the light propagating through the fiber, and del, symbol del, as a relative refractive indexes difference. Okay. So this is a single mode fiber structure is. You can see that this cylindrical shaped structure is core, inner, and this outer is your cladding. So this is your mode. So this line which is drawn here, so this is your mode. Okay, so this is your principle of total internal reflection, where light from here falls onto this layer of the boundary of your core and cladding. See here, boundary of the core and cladding, and it reflects back, and it hits at the top, and it goes the bottom. It's at the top, goes and bottom, and it goes on. As you see in diagram, it will be at the top and the bottom, but it is cylindrical in nature. The shape of the structure is cylinder. Okay, this is the central axis. This dotted lines is present. This is your axial of the fiber or the center of the fiber. So when light passes through this, it gets reflected here. Why it gets reflected is that I'll show you. You can see the total internal reflection. So I need to travel my light wave entirely inside the core itself. If I send it in cladding, what will happen is that it will absorb the light signals. It will not reflect back. Okay, it will only refract. So if refraction occurs, there will be loss of your signals. So that's what here the optical fibers always uses your TIR principle, total internal reflection. So light from here falls onto this, gets reflected, goes back, falls onto this, reflected, goes onto this, reflected, and goes on till the end of the fiber. So at the end of the fiber, we'll be having receivers. So single mode fibers specifications. Only one path is available. You can see that only one path. So this is the path, arrow mark. You can see here, 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 here. This is the arrow mark. P number is less than 2.405. It should be always. The core diameter is small. The dispersion is very less. It can be used up to 1000 megahertz of bandwidth. Useful for long haul communications or long distance communications. The drawback is that the fabrication of this single mode fiber is difficult and it's costly. Okay. So now let us see multi-mode fibers. When you see the difference between the when you see the difference between single mode and multi-mode fibers, you can easily understand what is a multi-mode fiber is and a single mode fiber is. So I'll show you single mode fibers again. You can see that core cladding is present. Core is present inside the cladding. A mode of propagation occurs from the fiber and it transmits only one mode. Okay. You can see multi-mode fibers. In multi-mode fibers, the core, you can see core diameter is enlarged as compared to single mode. You can see that this is smaller, core is smaller. Here, core is larger, such that it accommodates more modes of propagation. You can see that this mode reflects from here, goes directly here, and goes here. Then another mode here, and it reflects, goes here. This one here and goes here and goes. So this is your core axial, axis of the core, axis of the fiber, and there are more than one modes of propagation in the multimode fibers. So this is your core and this is your cladding. So the core diameter will be greater here. So now let us see what is this multimode fibers is. So if more than one mode is transmitted through an optical fiber, then it is called as a multimode fibers. The core diameter or the core radius will be larger as compared to single mode fibers, such that it would be easier to launch optical power into the fiber and facilitate the end-to-end connection of similar powers. So some of the properties is that more than one path is available. You can see multimode fibers is having more than one path. V number should be always greater than 2.405. For single mode, it should be less than. So these are the two different types of modes of fibers. So any queries in the types of modes of fibers? If queries, you can type in chat box. But because we are going to see the next topic, which is configuration of optical fibers. So far we have seen types depending upon the modes of propagation. If only one mode is being propagated in the single mode and the characteristics. And if you want to transmit many modes, more than one mode, we call it as multi-modes. The core of the optical fiber for multi-mode is larger, whereas the core of the optical fiber for single mode is smaller because it needs to accommodate only one mode. Okay. Thank you, Mukesh. Thank you, Sai Ganesh. Okay, we'll proceed on to the next topic, which is configuration of optical fibers, which comes under the types of fibers based on refractive index profile or RI profile. Okay, so based on the RI profile, the fibers are classified into step index and gradient index. So we'll see that step index and gradient index is what. Okay. This step index and gradient index occurs both in single modes and multi modes. I'll show you the diagram. Then you'll be able to understand what is. Wait a moment, I'll bring the diagram. Kindly await. I kept the image somewhere. I'll bring it and I'll paste it here. I'll show you all the step index and graded index in the same slide, such that you will be able to differentiate them easily. Yeah, I got the step index and index file. So I'll show it in the presentation. Kindly await, such that you can understand the difference between the step index and graded index easily. I think this we had seen on this slide. Yeah. Based on the refractive index, fibers are classified into step index and gradient index. So this step index, you can see that here at the top you see N1, N2. So is the step index I show. Figure A, figure C is a step index in single mode and multi-mode. Don't worry about the second diagram which is being drawn. Leave that. So I'll explain how it propagates. So here you see that we have a center. You see the center, which is your core axis. Okay, axis of the core. So that to N1. Okay, you can see that N1 is your refractive index of core. N2 is refractive index of cladding. So the radius of core and radius of cladding determines the step index. Okay, so you can see that here there is a shape. The movement from uh, N1 to N2, there is a step-like structure. You can see that. You can see that there is a step-like structure from N1 to N2. If that is the case, this you call as step index fiber. See, you can see in the single mode step index also, N1 and N2, you can see that there is a step structure when moving from the core to cladding. This resembles a step-like structure. So this is called a step index. And we have some conditions for that and characteristics that I'll show you. So this is step index. So whereas when you see the gradient index is that the multiple gradient index. You can see that the N1 and N2, so which is your refractive index of core and cladding, is being given by only the radius, which is A. Okay. So if this is the case, we call it as gradient index. So step index, you can see that the structure of step index will be that the core and cladding difference will be in the form of steps. Whereas in gradient index, there will not be any step size. Other than that, the gradient index is defined by the radius of the core. Okay, you can see the radius of the core. You can see that there is a gradual, so which is gradient index. So this diagram shows you three different forms. One is a single mode step index. We are going to send only one mode. Okay. Only one mode. So step index. So this is the center of the fiber. So A represents the radius of core, B represents the radius of cladding. You can see the difference in single mode and multi-mode step index, A and C. So A is larger in multi-mode step index, whereas A is smaller in single mode step index. B will remain the same. Okay. So whereas when you see in multi-mode step index, many modes of propagation are occurring. You can see that as I've shown you, many modes. 1, 2, 3 modes are moving. Okay. In this fashion, see the fashion in multi-mode step index. So depending upon the step size, since the step size is like this, in the form of steps, which is 90 degree. So the light also will propagate in 90 degree. Okay. So whereas when you see gradient index, there is no 90 degree or there is no step. It is a gradual radius. So the wave also will propagate in a radius. You can see that at an angle other than 90. Here angle at 90, here angle other than 90. So this is the difference between step index and gradient index. So a typical illustration of the mode of fibers. Okay, you can see it here. Step index fiber will be like this. You see from the outer. Okay. Gradient index fiber will be like this. Okay. And single mode fiber, single mode step index will be like this. So these two are multimodes, and the top two are multimodes. This last one is a single mode. Okay, single mode step index. This is multimode grid index, multimode step index, as in this fashion. Okay. So the input pulse will be in this fashion. The input pulse for grid index multimode will be in this fashion, and for single mode step index will be in this fashion. You can say the core radius of the core is larger in the first picture. The radius of the core is smaller in the last picture. So these are the differences. Here is a small example as how multimode step index and multimode grade index will differ. The multimode step index will be moving at an angle of 90-degree, I said. So the center white is your core, blue is your cladding. The multimode step index, it will move in this fashion, whereas in multimode grade index it will move in this fashion, like this. Yes, since it's cylindrical. So now let us see what is a step index. So step index, the refractive index changes in a step fashion from the center of the fiber, the core, to the outer shell, to the cladding. It is high in the core and lower in the cladding. The light in the fiber propagates by bouncing back and forth from core cladding interference. So it is the boundary. So the step index fibers propagates both in single modes and multimodes within the fiber as shown. So the light rays propagating through it are in the form of meridional rays, which will cross the fiber core axis during every reflection at core cladding boundary and are propagating in zigzag manner. So I'll show you the zigzag manner. So this is your step index, zigzag manner. In step index, next is the dimensions of step index. So with careful choice of material, dimensions and wavelength, the total dispersion will be smaller, that is less than 0.1 picoseconds. Making this fiber suitable for use with high data rates. In a single mode fiber, a part of light propagates in cladding. So the cladding should be always thick and has low loss. Typically, the core diameter for single mode fibers will be 10 micrometer. Core diameter will be 10 micrometer. Cladding diameter will be 120 micrometer. So the handling and manufacturing of single mode step index is more difficult, so as discussed earlier. So next is the step index multimode. Since step index single mode is difficult, we move on to multimode step index. So the multimode step index, as I had shown you, so which propagates in many modes. So how to calculate this modes is that mn will be equal to v square divided by 2, so which is equal to 4.9 dn1 square root of 2 del divided by lambda the whole square. So lambda is the wavelength, del is the refractive index, 4.9 is calculated from v value. So where d is the diameter of the core of the fiber which we are using, v is the number or the normalized frequency. So this v number, how do we calculate? So in some cases I told you it should be less than 2.5 49. It should be greater than 2.49 in some cases. In single modes, less than, and in multimodes, greater than. So how to determine that V number? V number can be determined by 2 pi a divided by lambda into numerical aperture, where a is the fiber core radius of core fiber A. Lambda is the operating wavelength, and this in terms of refractive index also we can write. So which is V is equal to 2 pi a divided by lambda n1 into 2 del the whole power half, or square root of 2 del. So where n1 is the core refractive index, del is the relative refractive index. So with this we can find V number. Next is the gradient index. Refractive index is the core as you move on from the here the refractive index that is in the optical fiber core varies as you move from the center. Okay. So the refractive index of the core is made to vary in the form of parabolic manner in graded index. So that's what we get a radius of curvature. Such that maximum refractive index is present at the center of the core. So the refractive index profile with reference to the radial distance from the fiber is given as this. Okay. So radial distance r is equal to 0, n of r is equal to n1. Okay, refractive index will be equal to n1. So when it is less than a, n of r will be this n1 into 1 minus 2 del r by a the whole square is the whole square root. And if r is greater than or equal to a, okay, n of r will be equal to n2, which is n1 1 minus 2 square root of 1 minus 2 del. So where n1 is known, n2 is known, a is radius of the fiber. So this is how we find the refractive index profile of gradient index fibers. So this is a gradient index fiber as shown. Core axis, we have core. So gradient index moves along the radial axis. Each dashed circle represents, you'll see the dashed circle represents different refractive index, which is decreasing as we move away from the center. As we move away from the center, it is moving. Ray incident on these boundaries between Na minus Nb and Nb minus Nc is refracted. As the ray moves on inside the core or inside the fiber, it gets refracted. This is continuous till the ray tracing is done. Ray tracing is done as such, as like this ray tracing is done. The light rays is propagated in the form of skew rays or helical rays, which will not cross the fiber at all. As you see here in this image, you might be thinking here it is being merged or here it converges. It is not at all. It moves in these two fashions, either in the form of skew rays or helical rays that do not cross the fiber axis at any time. Okay, and the propagating wave will be around the fiber axis in helical shape or spiral manner. So the effective acceptance angle of gradient index fiber is somewhat less than that of step index fiber. So the disadvantage is that since the effective acceptance angle of GI fiber is lesser, the coupling of fiber to the light source is more difficult. So now we come to the end of this presentation of part 1. So any queries, type in chat box. I'll give you 4 or 5 minutes time. If there is any queries in this presentation, you can type in chat box. I'm ready to address all the queries for this session. Then we'll proceed on to the next part. Yeah, since there are no queries for the part 1 presentation of unit 1, I proceed on to the part 2. Okay. So let us move on to unit 1 part 2, which is about mode theory of circular waveguides. So in this presentation, we are going to see three different concepts. One is the mode theory of circular waveguide, overview of modes, and key model concepts. The mode theory of circular waveguide starts with the ray optics limitations, okay, which does not deal with coherence or interference phenomena. So it doesn't give the field distribution of individual modes, does not show coupling of power between modes of waveguides. Hence, we move on to the mode theory. Okay. The drawbacks of the ray optics is these 3 points. So, hence, mode theory was being proposed for a circular. So, for this, we need to know the different types of rays available. Okay, since we need to eliminate the ray theory. So, there are two different types of rays. One is meridional rays and one skew rays. So we are going to see about both of these today. Meridional rays are confined to the planes of the fiber, that is, planes containing axis of symmetry of fiber or the core axis. So we are seeing the core axis of the fiber. So the meridional planes are confined to that core axis in symmetric fashion. So a meridional ray propagates in a single plane along the fiber axis, so it is easy to track. It will propagate only a single plane. So they are being given as bound rays and unbound rays. So bound rays are that they are being trapped in fiber core according to Snell's law of reflection and diffraction. Unbound rays are the rays that are refracted out of fiber core according to Snell's law of reflection and cannot be trapped in core. So once it moves out of the core, that is by not obeying Snell's law or the TIR principle. If the light moves out, it cannot be trapped inside the core and it can be propagated further. So that type of ray we call it as unbound rays. So if a light which is being propagating can be trapped within the core fiber, we call it as bound rays. So now let us see the types of rays in skew rays. You can see that the light propagates without passing through the core of the fiber, as like this in this fashion. You can see the wave, the light wave falls at the core and it moves in this fashion. It doesn't touch us at all. It doesn't pass us through the core of the fiber or the axial of the fiber. Okay, and it goes on like this fashion. Okay, so it is not confined to a single plane, but follow a helical path along the fiber. Following a helical path. So this is a helical path like this, without actually touching the core of the fiber. So this type of rays we call as skew rays. So these are difficult to track as these rays do not lie in a single plane. So this is the shape of the skew ray. The direction of ray changes by an angle to gamma at each reflection. So what is that gamma? Is that gamma is the angle between projection of ray in two dimensions and radius of fiber core. Depending upon the radius of fiber core and the projection of ray in two dimensions, the gamma is being obtained. So the direction of ray will change by that angle. So skew rays shows smoothing effect on distribution of light transmitted even if light launched in fiber is not uniform. Skew rays shows smoothing effect on distribution of light transmitted even if light launched on the fiber is not uniform. The numerical aperture of skew rays, NA of skew rays, is always greater than meridional rays. To keep in remembrance. How do we find the acceptance angle of skew rays? You can see here you have a fiber, we have a core, we have a cladding. So the skew rays doesn't touch the core axis, so it propagates in a manner with in a helical path. Okay, so this is the light ray falling at first at point A and next at point B, and it goes on to point C. Okay, we have the refractive index of core as N1, refractive index of cladding as N2, the angle being created as theta, gamma is your angle of projection and radius of the core, so that gamma is here, 2 gamma. Then with that we can easily find acceptance angle, okay, which is given as RB. RB is distance of the distance between the uh, point where the wave hits the core, sorry, with wave hits at the core cladding difference from that point to the center of the core is R, and distance between these 2 points is RB. And where A is the first point where the light wave falls, or the first point where the reflection occurs. So AP. So this RB divided by AB cos phi is equal to RB by AB. With this we can find it easily. So how do I find this? Is that RB by BT, T is the total diameter of the core. So RB divided by BT into BT by AB. With this we can find cos phi. So cos gamma sin theta is equal to cos phi. So cos gamma sin theta is equal to cos phi, which is square root of 1 minus sin square phi. So under the limiting condition of phi becomes phi c, so which is critical angle. Or the angle of acceptance. So the angle of acceptance is sin phi c is equal to n2 by n1. So with that we can relate it here. Substitute, we get sin theta as n1 divided by n0, cos phi divided by cos gamma is equal to n1 divided by n0 cos gamma, square root of 1 minus n2 square divided by n1 square. So this value, square root of n1 square minus n2 square, is numerical aperture. So we can substitute that it here. So n0 sin theta cos gamma is equal to numerical aperture. Or you can find sin theta, or the acceptance angle, is equal to numerical aperture divided by cos gamma. This is what skew rays and meridional rays is about. So next topic is mode theory for circular waveguides. So in order to understand the mode theory for circular waveguides, we should be familiar with the modes of propagation of electromagnetic field in circular waveguides. Okay, we are taking 3 different modes: TE0, transverse electric 0 mode, transverse electric 1 mode, transverse electric 2 mode. So how it is being present? T mode, T0 mode in core. You can see that like this. So we have the optical fiber. N1 is the refractive index of core. N2 is the refractive index of cladding. So the boundary separates the core and cladding. So the harmonic variations is the variation of the pulses propagating from one point to another point. In TE0 mode, your propagation will be like this. In TE1 mode, it will be like this, in this fashion. In TE2 mode, it will be like this. You can see the difference of harmonic variations. So these field patterns are important. So there are three categories of mode. One is the bounded modes, second one refracted modes, third one leaky modes. Bounded modes are those modes which are confined in core of waveguide, like this. Which are confined to waveguides. It's called as bound mode. In refracted modes are those which are scattered out of cladding due to roughness of surface or absorbed by the coating of clad. When a light signal or light wave propagates, it will be absorbed by the cladding. So in that case, refraction occurs. So that mode we call as refracted mode. Third one is the leaky modes. Leaky modes are those which are partially confined to core, region that attenuate continuously. Meaning is that as the light wave propagates through the core fiber, they continuously attenuate. Means losses. These are the three categories of modes in mode theory. So now let us see. When we say confinement of modes is called as bound modes, we should see the condition for that. On what condition? The confinement of the mode occurs. So that depends upon the propagation constant beta. Okay. So beta should be n2k less than beta less than n1k. Meaning is that if beta is less than n2 into k, power leaks out of core into cladding region. There will be significant power loss due to leaky modes. The modes will sustain very small loss throughout the fiber propagation. If beta is less than n2 into k. A is a reflection. So any queries till this? Why? Because the next topic is completely on Maxwell's equation that you had studied already. I think so. Yeah. Next topic is mode theory for circular waveguides. Under that, we'll be seeing key model concepts. So I'll stop it till here. We need to see the Maxwell's equation, how it is used with optical fiber, wave equations for a cylindrical optical waveguide, TE mode, TM mode, and TEM mode. Then its solution. Then the model equation. Okay. So this we'll see in next class. So for the time being, any queries? Okay, kindly await. If no queries, kindly await. I have an information to give you. Yeah, wait, and video as to show you the difference between single modes and multimode, how they are being used in the industry.
Meter and OS2 being 0.4 decibels per meter. Crazy transmission range. The specialist equipment information. Cost of a single system is higher multimode. The same cost to install. Multimode fiber. Dictate in an opposite way to counter multiple or many modes of transmitting down its core, all of which travel at different wavelengths or in a different path. The light source is source. Thus the light is similar to that of shining a torch into the core. Subsequently there is global dispersion, loss, of light as it travels. For this reason, Multimode is the same distance capability as single mode. The cores of multimode fiber are considerably larger than single mode. Four of the main categories are 125, and the legacy OM1 is 62.5 by 125. Notice that the cladding for all fiber cables remains the same and only the internal side changes. The five categories of multimode fiber are OM1, OM2, OM3, OM4, and OM5. Each category is an improvement on its predecessor. Therefore, this results in a greater ability to transmit. Are able to transmit the same speeds as the previous rate, but over differences. Single mode is multi-mode fiber summary. Core speeds. Single mode are 9 by 125 microns. Multi-mode are 50 by 125 microns, and in the OM1 category 62.5 by 125. Transmission. Single mode uses a single mode of light transmitted via a laser light source. Multi-mode uses many modes of light via an LED light source. Consider techniques. Single mode is commonly used to 2 meters and often beyond to 10 kilometers. Multi-mode is 550 meters performance and therefore may be used internally or small components. For a free quotation, please visit our website and cabling.
Yeah, I hope you would have utilized a good video on the difference between single mode fibers and multi-mode fibers used in industry standards. Okay, still if you have any queries, you can type in chat box. thank you for your patient listening for the second session. So in chat box, I had shared you the attendance link, and in the attendance link, I had given you a question as to state whether do you possess an PC or a laptop at home for giving you optical communication software for conducting laboratory purposes. So give your genuine answers. If you are having, put yes. If you don't have, put no. So depending upon that, I will be sharing you the link for software such that you can install in your PC or laptop for performing optical communication laboratory. Okay, thank you.